Are you getting the audio all right? All right, good morning, everyone. I'm Anil Agrawal, might have been introduced to me. Actually, I work in the area of structural engineering, just like most of you are. And I specialize in the field of structural fire safety, how to design structures for fire conditions. So generally for buildings, fire safety comes as a second thought, as an afterthought. Generally, as structural engineers, we are not taught how to design structures for fire, right? So even if you see IS 800, IS 456, you will see fire being mentioned only tangentially, only briefly somewhere in the as one of the loading conditions that you should consider, but it's not really one of the primary loads that we typically design our structures. Or even at IIT, we don't teach our students how to design every single structure for fire. Question arises whether fire is it worth it? Is fire really a major concern as far as structural safety is concerned? Because ultimately we are concerned about structural safety. But if we think further, we are not only concerned about structural safety per se, we are concerned about people's safety and safety of our infrastructure, or whatever, the investment that we have put in to the infrastructure. That, of course, with the help of structural safety. So structural safety is a way to get there. Structural safety in itself is not the ultimate goal for structural engineers. It is the safety of our infrastructure, meaning our investments. That is secondary, and primary one is safety of people, right? So when we think from that perspective, then fire safety becomes critical, correct? So then what role does the structural engineer have from fire safety point of view? That is a critical question. Now that, okay, we understand that it is important, fire safety of structures is important, but what we as structural engineers can do, or is there something that we should do? And that is kind of a debate that goes on in the industry has been going on for a very long time. And the reason for that is that structure can be made fire resistant, not necessarily with the help of structural solution. Sometimes a solution which is kind of seeded in the architectural drawing or architectural design, or maybe some kind of a chemical processes, or maybe some kind of an active fire protection system, or just having a very efficient fire safety department, firefighters. All these things can help make the structure safer. So it is not necessarily that structural engineers have to design structures to make them fire safe. Many of these things can be used as a secondary, tertiary, and so on, kind of a walls or kind of safety systems, which will prevent the structure from undergoing significant damage or collapse under fire, right? So because of that, there is a dilemma in the mind of a designer or in the mind of the owner of a structure, whether we should go for a structural solution for fire safety or we should go for a other type of a solutions. Some of them are passive, some of them are active. Active ones, somebody can tell me some active fire safety systems that you might be familiar with, what you might know as active fire resisting system? Sprinklers, right? So sprinklers are active, basically. They detect fire, or smoke detectors, for example. So smoke detector. So sprinklers typically work based on heat. They detect heat and then they trigger, and then the water starts coming, or smoke based detectors can be there. They can sound alarms so that fire department can be informed, and then they can. So fire department itself is an active fire protection system, right? The entire fire department, the entire municipality, that division of municipality. But passive fire resisting system would be what? Fire? No, fire extinguishers are not really, they are not classified as passive. They are also active in a way. They need somebody to operate them, but still they are active. Passive would be something, so that just stays there. Passive is something that just stays there and does the job, right? You won't even know that it is doing something. So for example, here in this building, you might see this black paint is there on steel members, right? And which is hiding the fire protection system underneath. So behind this black gray paint in the beam, you can see at some places some white powderish thing is coming out. That is because some water has gone into that one, and then basically it has kind of dissolved some of that liquid. It's not supposed to, but maybe there are some issues there. So what happens is that there is a white paint painted on top of the steel member, all these steel members, which is quite thick actually. It's not just a paint layer. It's like typical paint layer is in the microns, like in a few microns, but that is a few millimeters thick paint layer. It is known as intumescent paint, right? Similarly, what you see here is this is gypsum board. It does not have a fire safety purpose, but this board is very good for fire safety also. All these dry walls that you see, internal walls, these are all very good fire safety mechanisms. So there is a member sitting inside this, right? And if there was a member sitting inside this, sometimes it is sitting inside, sometimes it is not there. These walls are protecting that member from fire, right? That may not be the purpose in this building, but typically, where do you see these kind of a dry walls? These are dry walls. These are known as dry walls or fiber walls. Where do you see such kind of walls being used often? In what kind of buildings, structures have you seen them? So in this building, right? Auditorium. Sorry. Acoustics is one application. I'm talking about what type of buildings or structures you might have seen. Yeah. So in cinema theaters, they use this kind of a blanket kind of a fabric kind of a material typically, but that is not what I'm referring to. I'm referring to a building where it is used for fire safety. Where might have you seen it? This kind of a thing.
Pharma industry.
Pharma industry. In the typically we don't fire protect steel structures, steel sheds. Generally, fire protection is not applied until there is a specific requirement. So far, I have not come across. Maybe some chemical plants, sometimes they have to do it up to certain height. It's not usually the requirement. And when we do that, nowadays for steel structures, typically we do the intumescent coating. We don't do this kind of a facading, this kind of a covering with some kind of a board. Anybody where you might have seen it, this is basically a gypsum board, gypsum with some fibers added to it, you know, so stabilize it. Where you might have seen the use of gypsum board.
Shopping complex.
So shopping complexes, most of the shopping complexes, how many of you are from Hyderabad? I can give you examples from Hyderabad. So most of you are not actually from Hyderabad. Okay, so if you go to any big shopping mall, let's say here there is a Sarath City Mall, I think that's one of the biggest ones, or in Orbit Mall that used to be popular. So most of those structures are proper steel structures, and steel typically requires extra fire protection, and that gypsum board is placed around steel members where you don't see steel members. So it's a steel structure, but you don't see steel because it's all covered with this kind of a board, right? So commercial buildings are that way. Some steel buildings are also used, are built. They are relatively uncommon. Steel buildings are not that uncommon, but they use similar kind of structure too. So fire protection becomes critical. Fire protection has various applications, various reasons for it. This type of fire protection is called passive fire protection, right? So from structural engineering point of view, especially if you are dealing with concrete, I'm coming to this topic. I'm just kind of shooting all over the place. We'll come back to this one. So when you are dealing with concrete, active is the same. Active is same, sprinkler system, fire department, all those things. Passive, what is available as a passive fire protection to you when we talk about concrete structures? Where is the passive fire resistance coming from in a RC column or RC beam? Let's say it's a steel column. I gave you an example. You can do intumescent coating that way, the way they have done it in this building. I mentioned white paint. So beneath this gray paint, there is a white paint. You know, so if you walk outside, there are members, this diagonal members. Somewhere you might see some corner has chipped off and white paint is visible. Yeah? So that is one for steel. Similarly, they can do this gypsum board kind of a encasing. That is another one. These are the two most popular types. There is another spray applied and all that I'll not discuss too much. For concrete, where is the passive fire protection coming from? What is the option?
Silica, which is there already inside the concrete.
Yes, concrete itself, right. So very good. So basically, concrete consists of aggregates and cement, right? And both of them, the cement material and the aggregates, small and large aggregates, they have very good fire resistance themselves. Not as good as gypsum, for example, but they are pretty decent fire resistant materials themselves. They have a poor conductivity for heat, right? And they have a lot of thermal mass. They absorb a lot of heat. So for concrete, the concrete mass itself acts as passive fire resistance, right? Now, when we design concrete structures, we have to put reinforcement, right? when we put reinforcement, typically what happens is that that reinforcement that we put in RC structure becomes the weak link in fire conditions. When we, let's say, put steel bar. So if we are designing a beam, typically when we design an RC beam, we put the steel bar definitely in the bottom, like positive reinforcement. That is the bare minimum requirement. You can put negative reinforcement also, but positive reinforcement is a primary requirement. When you put positive reinforcement, that is bottom reinforcement, in a beam, you have to be mindful that the temperature in steel does not exceed a certain value. If the temperature in steel exceeds a certain value, that becomes a problem for RC beams, right? We will go into that detail a little bit. Similarly, when we put FRP bars, we have to be thoughtful, or we should be careful that the temperature in FRP bar also does not exceed too much. So, but a rule of thumb could be that you can just increase the cover, right? So if you increase the cover, you can delay the time it takes for temperature in FRP bars to exceed a certain value. So cover, typically what parameters govern the cover thickness for RC beams? Those who are not IIT Hyderabad students can maybe answer. Sorry?
Fire rating.
Fire rating. So fire rating is used to control the cover thickness. What else? Sorry?
Thickness.
Thickness of the slab governs the cover thickness. Why should the thickness, total thickness, control how much cover thickness you have to have? No. So fire rating, fine. So fire rating, as I had mentioned, greater the cover you have, more fire rating you will get, because it will take heat longer time to reach steel. That is reinforcement. What else governs the fire, the atmosphere or durability considerations, right? So the technical word for that is durability considerations. What does the durability consideration mean? We don't want our reinforcement to corrode.
Yes.
Correct. So if we want to have a certain amount of life for the reinforcement or for the structure, and want to prevent it from corrosion, steel reinforcement I am referring to, so we need to provide a certain amount of cover thickness. If the cover thickness is less than that, the atmospheric effects, which is basically your acidic environment, carbon dioxide or whatever, it can start to ingress. Yeah, so it can ingress into concrete, and how deep it can ingress, that depends on what environment it is exposed to and how long you have exposed to. So then for a certain period, you have to give at least bare minimum amount of cover thickness, right? So if it is more humid type of an environment, if it is more acidic environment, then you have to have a more cover thickness, right? So these are the 2-3 things that we should think of when we talk about fire resistance of RC members designed with FRP, right? Or reinforced with FRP, right? So I am assuming that FRP you have been discussed, like for last 5, 6, 7 days, you have been learning about FRP bars. They are used in RC structure. So I'll not spend too much time on that. I think fire has not been discussed in much detail so far, especially fire as a load. So that's where I'll focus primarily, right? So basically, first we will learn about fire, and we will spend quite a bit of time on knowing what fire load is. We are taught about live loads, we are taught about dead loads, how they act. They are all gravity loads. Then we are taught about wind and earthquake loads, which are lateral loads. What does fire do to a structure? That we hardly learn about. So we will discuss, we'll give quite a bit of time discussing that. Then when we design for fire resistance, what should be the objectives of designing for fire resistance? So objectives are, again, this is a little bit of gray area. There is no consensus in some of these objectives. We'll discuss in which way the debate is going and how do we typically handle that issue. And then how do we test for fire resistance? So for fire, mostly the situation is such that designing protocols are not established yet. It's still an ongoing research. So many times when we have to design something, we have to test it. So this is called designing by testing, right? So in the course, you may, if you read the course carefully, somewhere some small subheading will be written, designing by testing. Even in IS 800 mentions it, designing by testing. So if not enough literature is available, if you cannot say for surety this is how it is going to behave, the one way to know whether it will behave that way or not is to test it. So generally for fire, so far, designing by testing is the way to go. For other traditional members, RC, steel, protocols are available, designing provisions are available. You can design it according to that. But when it comes to RC with FRP, protocols are not in place yet. So whatever knowledge we have, I will try to share some of that with you. But eventually, the gold standard is designing by testing. Test the member and know whether the performance is adequate or not. And then if we don't want to do the test, we have to think about the alternatives. So then we will discuss some of that. This is where we will discuss what you have to consider when we go for the alternative route for designing, and then what are the protocols or what are the methods that we can follow for designing, right? So for fire, when we deal with fire, has several phases: initiation and ignition. Then there is a compartment fire, basically how it grows. Several parameters influence the behavior of the or growth of the fire. Then there is a growth phase, post flashover, and so on. Then there are a variety of fires that we can discuss, and what considerations one have to think of when we talk about fire spreading from one compartment to another compartment. That becomes critical. And then how to simulate the fire effects. So what is fire? Fire is essentially just heat, right? That's what it is. But heat does not come into any of the equations that we deal with. As structural engineers, there is no heat term in any of the equations. We have F is equal to ma if you are dealing with dynamics. If you are dealing with statics, sigma F is equal to 0. These are the equations. Where is the heat term there? So how to bring in the heat term there and how to bring in the effect of heat, that we will discuss. Okay, so what does fire need? What does fire need, or what does it need to start a fire?
Ignition temperature, an element to get burnt.
Fuel, temperature, and oxygen.
Right, very good. So basically, you need three essential components. One is you need initiation. Initiation means somebody should be putting in the effort, right? So that is your initial heat. So you need a source of heat somewhere. So even if I put a combustible material, typically on its own it does not ignite. If I take a diesel, or if I take petrol, I can put the petrol spread on some surface. It will not ignite automatically unless I put a source of heat to it, right? If it were to ignite that way, it would have ignited already. So just the fact that I was able to bring the fuel to do the experiment, that means it does not ignite automatically. Sometimes it may not be the heat alone, but it has to be some kind of energy. Sometimes pressure can ignite, right? Pressure can create a ignition type of conditions. That too can be considered. Sometimes spark can be the situation which can create the spark, which is basically electric spark. Electric spark can, short circuiting can create the ignition. So one source of initiation has to be there. Then fuel is required, of course, right? Fuel has to be some combustible material. What qualifies as fuel? Which materials qualify as fuel?
There is some parameter about the calorific value.
Right. Yeah, so generally what we look at is the calorific value, but that is not the entire story. I'll discuss that very briefly. So calorific value, what does that mean? If I take 1 gram of a fuel and I allow it to oxidize, how much heat will it produce or how much energy it will emit? That is calorific value, right? Per kilogram, how many joules does it produce? That is simply the calorific value. So most of the materials, some are not, of course, most of the materials that you find around you, if they are oxidized, they emit heat. So oxidation for most of the materials is an exothermic reaction, and does steel burn? And some of you might have be familiar with this. So before you say that, yes, I will show you a video. So this is basically so this is steel wool or steel cotton, you can call it. It's basically thin shavings of steel that we have exposed to gas torch. We have basically lit it with a gas torch, and you can see that it starts burning, and it is sustaining the fire. It's not just burning and like locally burning and stopping. The fire sustains. This fire keeps burning through the wool, right? Because it's an exothermic reaction, oxygen is available. It's able to burn even steel, right? So even steel can oxidize and produce heat, which heat can help it sustain. So fuel has to generate enough heat so that it can sustain the fire. If the fuel does not generate enough heat that it can sustain fire, then that may not be a good fuel, right? Another thing is that it should have low thermal inertia for it to be able to burn. What does thermal inertia mean? Let's say I have a material that generates quite a bit of heat, but for the next part of it, for the part that has not burned yet, for it to heat up to the level where the oxidation will start, it absorbs most of that heat and the temperature doesn't rise. Which material property is high for that material? so that it absorbs a lot of heat and the temperature doesn't rise. Specific heat, very good. So if the specific heat is high for that material, it will have a very high thermal inertia, right? If it has a high thermal inertia, it will not burn easily. If the specific heat is high, it will not be a good fuel. Right? Similarly, if it is very dense, again, the same equation, specific heat multiplied by density for a given volume will be the amount of heat required for it to raise the temperature. So if the density is high, again, you would need more heat to rise the temperature. Oxidation will start at a particular temperature, right? So if the density is more, the oxidation won't start. So good fuels have to have a low density, low specific heat, and low conductivity, right? If it's highly conductive material, what is the issue?
Scattered all around the molecule.
Right, so it will diffuse. The heat will diffuse very quickly through the material, right? So that will be a problem, because if the heat diffuses very quickly, the temperature won't be rising. So for the
concentration of
right, so most of the fuels are not metals, because metals are very highly conductive. Here the metal was able to burn because we have cut this into thin strips. Thin strips, even though they have high conductivity, the heat cannot disperse very easily, right? Whereas most of the fuels are poor conductors of heat. Paper, cardboard, wood, right? Foams, all of them are poor conductors of heat. If it's a very good conductor of heat, the material won't burn. So all the fuels have to have these properties. That's how the ignition can happen. So generally, we deal with these types of fuels. We deal with wood, cotton. These are the traditional types of fuels that we used to deal with much more often. Wood, wool, cotton. Nowadays, we have to deal with other types of fuels also, which include polyester, right, and different types of plastics, and so on and so forth. So for example, if you look at the amount of furniture that is in this room, except for these tables, all the rest is plastics, right? All the other material, maybe that sofa frame is wood. All the rest is different types of plastics, you know. So plastics are, again, they have a very high calorific value and they are very good quality fuels, right? So when we say how good a fuel is, we have to look at the calorific value of the fuel. Calorific value is basically, as I had mentioned, how much heat it produces when a certain quantity of fuel, and quantity is kilogram, like mass, a certain mass of the fuel oxidizes, and that can be measured using calorimeter test. Then what we have to also look at is, let's say, how much FLED, fire load energy density, is present in a compartment. So if you want to say, let's say we are studying this compartment, what is the chance, or how much heat or how much fire, what kind of fire can this room be subjected to? So then we have to look at what is the fire load energy density in this compartment, which is nothing but all the masses multiplied with their respective calorific values divided by the area, and area is the room floor area. So basically what we are saying is, what is the total fuel available in this room, convert this to calories, right? So we know the fuel in kilograms, we'll convert it to calories, megajoules, right? That is delta HCM, that divided by the floor area. So that is a standard way of quantifying how much fuel it is. Now sometimes this may be not a very good parameter, because sometimes what may happen, the fuel may be compact, placed in one corner. It may not be very easy to burn. Say for example, the same, I'll give you the extreme example. Look at that steel. In that case of steel, it was in a cotton form, it was in a fibrous form, so it was able to burn. But if it was a solid steel, it won't burn. But that does not get into the picture as such. But typically such examples are extreme. Usually we deal with situations where the things are much more straightforward. Then what happens is that we have to calculate heat release rate. Heat release rate is basically essentially what we are looking at. When the compartment is in fire, when let's say there is a fire inside any building or in a compartment, we have to see how much heat the fuel can produce, right? So it depends on how much fuel there is, what fuel density we have, of course, and on top of that, total heat that it will produce will also depend on what density the material has, right? For example, and this may be counterintuitive, but again, drawing inspiration from the example of steel. If I take this solid wood, I try to light fire to it, right? I'll count the kilograms of this solid wood, And when I try to light fire, I would say, okay, these many kilograms of fuel is available. I'll calculate the calorific value and say a lot of fuel is available. But it will not generate a lot of heat at any given instant. Why? Because the surface area that is available for combustion is limited. Whereas if I divide this into small chips, I break this down into small chips, okay, and then store it in a, spread it out. Again, the same calorific value, but that will release heat very quickly, right? Every single chip can burn from 3-4 sides. So I have increased the surface area of the fuel. So if I increase the surface area of the fuel, you might be familiar with the internal combustion engine, right? So what happens inside the internal combustion engine? The fuel is pumped into it, but fuel on its own does not burn very nicely if you just pump fuel into it and oxygen from the other side. You have to, what is the word for that? Atomize it.
Yes.
Right? You have to atomize the fuel. Atomization, what does it do? It increases the surface area of the fuel. You have to break the fuel into small droplets inside the engine and surrounded by air on all sides. So then those tiny droplets, tiny microscopic droplets, then they can ignite very quickly. You know, so that's what matters. So density actually affects the heat release rate inversely. If it is a denser material, it does not allow the heat to be exposed, heat to be emitted, released quickly, and exposed fuel surface area. So the two are connected. If the density is more, the heat release rate is low, and if the surface area, exposed surface area is more, heat release rate is more higher. Right, so all these things in the fuel we have to look at, and then based on that we have to come up with some kind of a heat release rate for a different compartments. Now calorific values are available readily from the literature. You can find several references where different types of woods and different type of polypropylene and whatever, like polyester, for them the calorific values will be available, but heat release rate has to be obtained for your particular system. So
What is the difference with FLED and density of fuel? Because if we see FLED, then it is a measure of the energy stored. It doesn't.
Yeah, I got your question. So the question is, what is the difference between FLED and density of the material? That's what the question is, right? FLED is the density of fuel in the compartment. So for example, whether I take this furniture, whatever is available in this room, that, or whether I break this down into smaller pieces, the FLED will be the same. All I am counting is how much material is there, how much their inherent HC, delta HC is, and what is the floor area is. So FLED will remain the same, but surface areas and density of material, because it will change now. If I turn this into a powder, its density will be lower, its surface area will be increased, right? So because of that, the heat release rate can be changed, and ultimately what we are interested in is the heat release rate. Calorific values multiplied by with the mass divided by the area will be straightforward exercise.
FLED directly doesn't affect the heat release rate.
It has a role. It has a role.
It doesn't mean that if the room has more FLED, then the rate will be more, and it depends on the exposure.
Both.
Different state of.
So it depends on both. For example, if I have material which has a very low FLED, right? So in the room, if I have all the materials which don't produce enough heat, let's pick one which has the lowest heat release here. Let's say wood. Wood among all these materials has the lowest heat release rate or heat calorific value. So wood, same number of kilograms of wood versus same kilograms of plastic. So those plastics will produce, let's say, kilograms of alcohol or kilograms of petrol. So I put 20 kilograms of wood or 20 kilograms of petrol. Both things are same quantity. Even if they are, imagine that all other factors, all these things are same somehow, then still wood is worse. Wood is safer than petrol or safer than alcohol, right? So their calorific value matters. On top of the calorific value, in what form they are presented also matters. So that form factor comes from this. FLED is first parameter, but then density and exposed surface area are the other two parameters, right? So steel has very low FLED. It is pretty much not a combustible material, but if you play with these two parameters smartly, you can even generate enough heat to make it combustible. That's the point. Okay, so these two things have to be obtained from experiment, because every time the form shape will be different. The same foam, same material foam, if I make a big bulk of foam versus I cut this into smaller pieces, like that is used in the furniture, it will have a different type of a heat release rate. So I have to consider what is the exposed surface area and all. Generally, these can be done with some kind of a simulations. Tools are available. I'll discuss some of those tools, but usually experiments have been done. And basically what has happened is that over a period of time, people have done enough experiments that people have come up with some kind of a heat release rate for different types of furnitures, and that can be used as standard practices. So let's say we have somehow figured out that this is the furniture in a compartment or in a building, and for that furniture or for that fuel, we know what is the heat release rate. Like if the unit area is burning, how much heat can be generated by the burning of that unit area. Then the question arises, how will the fire in the compartment behave? What will be the behavior of the fire in the compartment? If you guys are taking notes of everything that I'm showing, don't bother. These slides will be shared with you, so you can you can note down important parts. Slide numbers are mentioned, so you can, if you wish, you can take notes against the slide numbers. So fire growth and heat release rate are then very closely related. What happens is that most of the fires actually start as a localized fire. So fire is initially, combustion happens, let's say a candle has toppled or a stove has toppled, or maybe some short circuit has happened. So it is usually in a local corner, in a room or a compartment or in a wiring of the building, which is again locally confined. One calendar catches fire, or one small temple, there is a lamp or something that catches fire. From there, the entire compartment will be engulfed in fire, because ultimately when we are talking about structural consequence, we are talking about a reasonably large fire. A small typical fire, a tabletop fire, that should not generally affect the structural, or should not concern the structure. So generally what we assume is, which is not a bad assumption or very unreasonable assumption, is that when there is a fire on a unit surface area or a unit floor area, it has, let's say that surface is burning. Now the exposed surface is the same. The fire will burn through the material, but the surface will not change, meaning that once a certain portion catches fire, the heat release rate is constant. The oxygen has to get in, the surface, that surface basically has to burn and then produce the heat. Right, and those vapors have to, whatever vapors or combustible material, that has to turn into vapor or turn into gases, combustible gases, and that is what flame is. So that is rate of heat release per unit area is typically constant when it is burning, when the combustion has started. So basically what we can say is that if we can somehow develop a relationship at what rate the fire spreads, right? So fire can spread in two ways. Here we are talking about a fire that spreads in contact. Right, so this table catches fire, then the next table will catch fire, then the next table will catch fire. So it will be through contact. So generally what we do is, even though furniture in a room or the combustible material will be scattered in a different configuration, and we cannot really figure out what will be the flow of fire or what will be the route the fire will take, typically we will say fire will spread in a concentric circles. So that is the philosophy we go with, because it's impossible to predict how each compartment will behave, right? So generally the philosophy will go with, let's say fire starts from one corner, then from there it will spread in a concentric circle until the entire floor or entire compartment is in fire. This is generally acceptable, except in cases where you are dealing with very large areas. So if, let's say you are in an airport lobby, a very large area, and there is some combustible material sitting here, then for several tens of feet there is no combustible material, there is no furniture, it's an open space, right? So in such scenarios it will be difficult to use this assumption and apply there. But most of the office spaces and most of the auditoriums, public spaces, this is generally a good assumption to make.
Is it depend on the airflow, how the oxygen is coming to that place?
Right now we are not getting there. We are saying plenty of oxygen is available. Oxygen is available all around. So when you are talking about a circle, oxygen is of course getting in from all sides, and no matter how big the circle is, oxygen is available everywhere. That is another assumption you can say. So this is what we call a fuel controlled fire. Oxygen is not is not a concern. Plenty of oxygen is there. It is the fuel, how much fuel is available. So as the fire is spreading, more and more fuel becomes part of the reaction. So fuel availability is controlled. Fire is spreading at a constant speed in the radial direction. So basically we are saying it is going in a concentric circle at a constant speed. So radius is increasing linearly with time. Sufficient amount of fuel surface is available, meaning that it never ends, right? It keeps increasing until the entire fuel surface is covered, right? So it's not like, okay, so I'm going in a concentric circle. 3 directions I was able to go in a concentric circle. The 4th direction, the fuel was not available. So I don't have to zigzag the shape. It's a circular shape. I'm assuming that. Okay. So heat release rate with that assumption can be worked out like this one, where the Q, that is the heat release rate in megawatt. What is what? Joules per. What is the unit of, what is the meaning of watts? How much is a watt? No, not calorie. I'm not asking you to convert into calories.
It is a unit of power, energy released per unit time.
Energy released per unit time, right? So we are talking about joules. Megawatt means megajoules per second, right? So megajoules per second, that can be calculated as T square by K square, where K can be calculated as, K can be given as fire growth rate. It depends on what type of fuel we are dealing with. And as I was saying, instead of doing all that previous calculation, all this calculation of delta HC, M, etc., and then trying to figure out heat release rate, we don't have to usually do that. These K values are typically available depending on what type of room we are dealing with. If you are dealing with a room which is filled with solid wood type of structure, we would say K value of something close to 600 can be taken, and units can be taken appropriately, second per square root of megawatt, right? So it is the kind of a work backward. If it's a fast growing fire, meaning that modern furniture is made of what? Plastics, polyurethane, different types of foams. These are all very highly combustible materials, right? So there the K value will be smaller. If it's a slow growing fire, solid wood kind of a material, then the K value will be larger. So that K value you can plug in. T square divided by K square will give you the heat release rate. So typically these kind of empirical equations are available that you can use. Lot of research has gone into this one. So then we don't have to really worry about calorific value of each fuel. If you're really interested in doing that, let's say I'm doing a forensic investigation of a fire. There was a compartment which actually caught fire, and I want to figure out how the fire might have traveled. Then it makes sense to go back to the previous slide and calculate the calorific value, try to calculate what density the fuels had, what surface areas were available, and do the entire calculation. But typically, if you are just trying to estimate what type of fire can be expected, you would simply go with this relationship, and these K values can be figured out based on what type of fuel we are talking about. Yeah.
How can Q and K be differentiated?
Differentiated means?
Like the heat release rate and fire growth rate. How are these two terms?
So fire growth rate is a constant. Fire growth rate does not change with time. It depends. It's a characteristic of the room. Not the material, just the material, the room. So a room would have, let's say, a mix of wood and this thing. Then maybe somebody may say, okay, K of 600 is when the dense wood is used. This is not a very dense wood. It's a relatively light wood. So I would, let me go with the value of something close to 400. Okay, so based on some judgment or something, but that will be constant value for a compartment. But then once you know the K value, you have figured out the K value based on, and these values are worked out by other people who have done experiments on them, and they have worked out what K value to take. Once you work out the K value, then you put that K value and figure out what heat release rate you have. So how much heat the room will be generated per second. That is what the Q is.
That means a room with dense wood will have higher heat release rate.
No, put the numbers. K is in the denominator, no?
Yes.
K is in the denominator of Q, right? So a higher K value means lower Q value. Fine?
Suppose if it is in a room, different materials are there.
Right. Yeah, so basically again, these two numbers I have reported from some sources. I've forgotten to mention the sources, but there are a lot of these values are available. Especially in India, we don't do so much research, but in Europe, they have done a lot of research over a period of time, where a variety of combinations of fuels, they have come up with these numbers, and some compromise, some averaging has to be done at the end.
The distribution of that in a room also.
Yes, so that we typically assume that distribution doesn't matter, it is randomly distributed. That's what you can assume most of the times, unless you are talking about a special case where all the wood was placed in one corner and all the chairs were placed in one corner. usually you can assume a uniform distribution, random distribution. Yeah. So what is the purpose of this? The purpose is that right now, which phase of fire we are talking about? We are talking about the phase of fire. Anybody? Not initiation. Initiation has happened. Fire has already ignited. Growth. We are talking about fire growth. So basically the entire compartment is not in fire. The fire is spreading within the compartment, right? So spread of fire within the compartment, that is the phase we are talking about. And we are trying to quantify how much heat that fire generates, right? So with time, the heat generated by fire will keep increasing because more and more area will be covered in fire. And here also we are assuming that as the fire is spreading, it's not like some part of the compartment has completely burnt out. That is never happening, right? So that is another assumption, that the fuel at any place where the fire has already ignited is available as long as fire is there. That fuel is not fully exhausted, right? So then what would happen is that if you look at this equation, let's say K is a constant, then if you plot Q versus T, what kind of curve would you get? Q on the vertical axis, and horizontal axis will be T. So you will get a parabolic curve, right? Quadratic. So as the time increases, Q will increase more rapidly. That's what we observe actually. So this is time on the x-axis, heat release rate Q on the vertical axis, and more the heat release rate will increase more rapidly as the time progresses. Again, don't forget the assumptions here. The assumptions are, we have not covered the entire surface of the fuel of the compartment. Wherever the fire is there, sufficient fuel is available, and there is no shortage of oxygen anywhere, right? Plenty of oxygen. Wherever there is a fire, there is plenty of fuel also available, so it will keep burning, right? Now, if the K value was low, meaning that the heat release rate was high, if the heat release rate was high, you would see that we would very quickly run through the surface area, right? Because heat release rate will be fast and the material will be catching fire very quickly. And at some point, we will cover the entire surface area that is available in the compartment and everything will start burning. And that's when we will reach a peak, a plateau. And beyond that, the heat release rate will not increase, right? So this will be a kind of a plateau. Similarly, but if you go for a very slow type of a fire, you would see that it will grow more gradually. And then, I mean, there is no reason why I should drop it here. That dropping basically means somebody intervened and shut down the fire. So somehow we were able to stop the fire. Otherwise, there is no reason why the fire should suddenly the heat release should suddenly stop. It should gradually die, you know.
But in the other previous two cases, it can happen.
No, it cannot shut down completely suddenly because the fuel, basically what we are saying is that the entire fuel got exhausted in an instant. That doesn't happen, right? So it will get exhausted gradually. So even if that has to happen, that would happen slowly. So this is the growth phase of fire. What we need to really pay attention to is only up to this part. So initial part is this kind of a parabolic curve, quadratic curve, right? That is the initial part of fire when the fire spreads from one corner or one place in the compartment to the entire compartment, right? And this also is assuming that fire spreads through contact only. So when this thing is lit, it cannot create fire at the other end of the table directly. It has to gradually pass from here to there, right? That is an assumption, along with all the other assumptions that I have explained to you.
Is there any quantity classification is there, or is there a quality, like that fast, medium, and slow? How we?
So in the previous one I have shown you, right? So these values, for example, so these correspond to different materials. So the fast one will be this kind, fast growing fire will be something that is made of cartons and this like light materials, but with the same amount of material, right? So that's how this classification is done, right? The Q becoming constant is the one that is basically when the entire surface area is covered, then we don't have to worry about it. The other parameter that we were so far assuming was always available in plenty is oxygen, right? So fuel is what we have discussed so far, and we are saying when there is a fire, the fuel is not exhausted yet, or will never be exhausted. The proportion where the fire is, that is fine, but at least we have discussed how the fuel keeps getting added to the combustion process. That part we have addressed, but fire, the oxygen part we have not really looked into. So oxygen is very critical, and in fact what happens is that most of the times, as soon as fire gains any significant size, where it starts to become hazardous to us. Oxygen is the one that starts controlling the fire, right? More than the fuel. So oxygen is a very critical parameter. If you see any typical building in fire, this is of course the picture taken from US, you can see the flames leaping out of the windows. What does that mean? The flames leaping out of the window. And especially in the top half of any window, you would see flames leaping out, not the bottom half, only always near the top half. So what is happening in the bottom half of the window?
The oxygen is
Right, exactly. So whenever there is a window, the bottom half, usually the oxygen is rushing in, the cold oxygen is rushing in. Since the cold air is rushing in, it kind of kills the fire. So in that part, you don't see any flames because that's a cold air that is going in. And all the kind of half burnt fumes, the fumes, the combustible material, that is not fully burnt, right? And it is thirsty for oxygen, where oxygen is available outside. So it kind of leaps out of the window and try to capture oxygen from outside. So that's what happens. There is a air inflow and there is a fire outflow out of a compartment. That shows the significance of oxygen, how critical oxygen can be to sustain a fire. If we can shut down oxygen supply, we can extinguish fire, right? How does fire extinguisher work? What does it do? It does not really
cut off the connection with oxygen.
Yes, it does not really cut off the fuel supply. It cuts off the oxygen supply. How does it cut off the oxygen supply? Either it by releasing carbon dioxide. So carbon dioxide is generally heavier than air, so it has a tendency to sit, right, go downward, and you spray.
A layer over the
Yes. So it basically kind of gives a protective layer, so does not allow oxygen to get in and kill the fire. Sometimes we use foams also. So there are other types of fire extinguishers which spray foam. So foam also does the same job. It basically stops, that's non-combustible type of foam, and it stops oxygen from getting in. So then what happens is that oxygen is the critical parameter, and oxygen is available in plenty outside. Inside the compartment, oxygen is typically restricted, limited, So generally in any given compartment, the oxygen that is inside the compartment is very small, not enough to burn most of the material in the room. Only a very small portion of the room needs to be burnt, or the furniture needs to be burnt before the entire oxygen is consumed, whatever can be taken, right? So we need oxygen supply from outside, otherwise fire cannot last. If you put a sealed room, no extra oxygen supply from outside, fire won't last very long, right? But people will also not last very long. Yeah. So basically what happens typically in a real fire, so we have talked about fundamentals, some basic assumptions and all. In a typical fire, there are these phases. There is an incipient phase, which is basically the initiation of fire, right? The fuel has not burnt yet, but fuel is being heated, you can say, right? So a spark has taken place, a candle has toppled or something. That is incipient phase. Then there is a growth phase. So basically ignition just has happened, and as soon as ignition happens, now the fire starts to spread from one corner or from one furniture piece to the rest of the compartment. Then there is something called flashover. Some of you might have heard of flashover. Anybody who was familiar with flashover? Yeah, I think if you have seen my presentation, of course, you would know. Then there is a post-flashover fire. Post-flashover fire is what is really, really critical from a structural point of view. And that is, these are the two areas that are of prime importance to us. That is where most of the fire safety community focuses. On top of that, then we also deal with decay phase of fire, wherein we deal with the fuel being exhausted, and slowly the fire starts to die. And if we take the compartment temperature, let's say average compartment temperature, because initially the fire will not be spread everywhere. So some portions will be hot, some portions will be cold. Let's do an average. So if you do average compartment temperature, you'll see it slowly grows, right? And this curve has somewhat similarity with what we have seen already for fire growth curve, the heat release rate, right? So as the heat release rate is more, temperature is also higher. And because of that, you will see that kind of a parabolic shape, right? Even though it's not really representing energy, it is representing temperature, but temperature and energy are closely associated with each other. So you can say that. But then there is a point called flashover. A flashover is a very interesting point. We'll get into flashover, but before flashover, we'll just discuss a few other things, how the fire actually spreads. So basically, typically what happens, one piece of furniture catches fire, right? So that's where the ignition was, and that's where the fire starts to take place. Now, generally what happens is that when that piece of furniture has caught fire, either the fire will start spreading to neighboring furniture pieces, but there would be typically a limit how far the fire would spread, because no room is filled with furniture everywhere, right? You would have a table sofa sitting in one corner, then you would have a television sitting in the other corner. So for the fire to reach from sofa to television, there is no direct connection, right? Sometimes there may be some carpet or something, but typically there is no such direct connection. So if there is no such direct connection, fire would remain constrained in that area, right? There is no direct jump for fire. But still, what happens is that because of this fire burning and producing a lot of fumes, a lot of combustible material, which is half burnt basically. Why is it half burnt? Because the room is kind of confined. The oxygen is not available in plenty, so everything doesn't burn fully, and it's a confined space. So basically what happens is that the top half of the compartment starts to get filled with these hot fumes of half burnt fumes, and the lower half is usually safer. So generally when we give drills for fire safety, we always ask people to crawl, right? When you're trying to escape from fire, don't stand up and walk. If the visibility is poor, typically we should kneel down, we should crawl, and at lower levels you will see better visibility will be better, you can see what is where, and also there is a less chance of somebody inhaling these toxic gases, right, the fumes. So generally we are supposed to be at a lower level where generally the air quality is better. Air quality is much worse at a higher elevation. Okay, and now as the material keeps burning, and as I had mentioned, even a small quantity of wood, you might have done some havanam or whatever, homam at home, and you might realize even a small amount of wood can produce so much of smoke, right? And if you do it indoors, you will realize that the entire room gets filled with smoke in no time, right? So basically what happens is that this layer starts to become thicker and thicker, and as soon as this layer starts to become slightly thicker, that's when all the active fire protection system should trigger in, which is your smoke alarms, your fire extinguishers, everything should work at this stage. If they miss this stage, for some reason they don't work, then they will not be effective later on. Then what happens is that this fire can be sometimes simulated. Basically what happens is that this air, which to us looks like smoke, sometimes can be very, very hot. It is basically half burnt combustible gases, right? So they are almost ready to burn, and these can be very hot. And if you want to simulate this one, many people have tried it. They divide the room into two parts, the upper half and lower half, and then they give them different temperatures, and then they can study the behavior of the compartment that way. It's called two-zone model. We'll discuss a little bit more on that one. Then what happens is that if, let's say, there was a fire here and there is no direct connection between this and this, still fire can jump to another piece of furniture that is sitting far away. That happens quite often, in fact. What happens here is that this plume and this layer of all the unburned gases, they start accumulating heat, because the heat is continuously being emitted from here. That heat is traveling and accumulating there, right? And all these burnt particles or half burnt particles, they are accumulating in that area. They generate a lot of heat. That heat radiates in all directions, not just upward. Radiation can travel in any direction, right? Convection mostly leads to travel upward, but radiation can be in any direction. Beyond a certain thickness that becomes enough mass or enough heat source there, that radiations can start coming downward on everything that is under it. So if there is a carpet in the floor, even though the carpet didn't catch fire directly, because of that heat that is coming down from above, the carpet can start catching fire, and that can lead to fire in anything that is kept inside the compartment. That is a phenomenon that is known as, what is the word? Flashover, right? So that is a very critical word. If you have taken a course on fire, you should remember the word flashover, right? So if you have taken a word, if you remember word flashover, people will assume, okay, you must have learned something about fire. So that is called a flashover point, right? What is a flashover point? Can somebody tell me? Just somebody from that row. Anybody? Flashover. What is a flashover point? Don't be so busy writing down. There's not much to write. What do you call a flashover point? It's written over there. I'm just trying to see if you are paying attention, or if I'm going too fast. What is a flashover point? Anybody? Any volunteers?
When the
Radiation,
1 second, I'll get
where which temperatures it is going to ignite.
the temperature at which.
Ignition.
No, ignition itself is not really flashover. The flashover point, I'll repeat it because that's a very critical aspect of fire safety and structures. You wanted to add? He tried first, maybe. You want to add? Hello? Yeah, you were saying you're trying to answer, right?
when the temperature in the compartment reaches a certain limit, then the material in that ignites without being in contact with the fire.
Right. So when the fire in a compartment in some furniture or some piece of fuel starts without being in direct contact with the flame, right? So some part is burning, there is a flame here, but some other part of the compartment catches fire without being in direct contact with that flame. That we call flashover, right? And flashover happens because there are this thick smoke which is hot. This accumulates and then it emits heat downward, which can ignite anything else, right? So this
So flashover is will designate with the time or
time, yeah. So it's a flashover time. At what time did the flashover take place, right? So generally, as you can understand, the flashover can happen only in a confined space,
Yes.
right? If it's an open fire, there is no flashover possible because there is no accumulation of fumes. The fumes will keep escaping the compartment or the space. So very large compartments.
in this event, material which is closer to the ceiling is not going to be burnt or it takes much more time to burn.
Yeah, so typically when we deal with modern construction, unless we are dealing with timber type of a construction, ceilings don't burn. Even though I gave an example of steel burning, steel doesn't burn, concrete doesn't burn, they don't oxidize in bulk quantities, so they don't burn literally. And maybe there may be some wiring or something that may burn, but that's okay, that's additional heat produced. What we are talking about here is typical modern construction where only the things that are not part of structure burn. Our structural components typically don't burn. When you are dealing with timber structures, then it's a different animal. The structure itself can burn. So we are not talking about that per se. But another important part is that timber, even though it may give an impression that it will be very easy to burn, all the earlier construction used to be in timber and fire was not that common. So what happens is that timber doesn't burn that easily as compared to all this foams and polyurethanes and polyesters that we keep in our compartments because of the density that wood has. So what happens in wood is, because of the high density, since that you have brought in this topic, I'll not have much time to discuss about wood. But, correct. So basically what happens, what wood does is not really what you could call burning, you would call it charring, right? So basically what happens is that even though there may be cracks and something in the wood where the fire can enter it, but it doesn't really happen very effectively, and you have a solid piece of wood, there the fire will be only interacting with the surface, which is a limited amount of burning that can happen, right? So if you have got a, let's say, floor, the slab will typically be steel masonry or something. If we go to 1800s, 1900s, the beams will be timber and the floor will be masonry, some kind of a masonry, some kind of arches or something. So masonry can't burn, it's the timber that can burn. But even if the timber burns, it will be burning only on the surface. Surface area is relatively restricted. It will burn very slowly. The calorific value is not very high for wood anyway. You saw the calorific charts, right? So wood was relatively on the lower side, solid wood. And then on top of that, it has not enough surface area, very high density. So the heat release rate is not very high, right? So typically wood, even though wood has got bad image in people's mind, it is not really a very bad structural material from fire safety point of view. Modern wood, plywood for example, that is a different story, or MDF, that's a different story. That is low density material. We chip it into small pieces, then we add what? Other organic compounds, which are themselves combustibles. Like all the adhesives, they are all organic compounds, epoxies, they are combustibles themselves, right? So that's a different story, and they are bad from fire point of view. But solid wood is not typically as bad.
And charring is in fact helpful for us.
How?
Like we usually do charring in the wood to increase its durability.
So that is another point wherein some people say, I'm not an expert in that one. I'm not saying that they are saying it wrong, but people say that it can increase its resistance against different types of pests. So for example, termite, etc., its resistance can increase, but that's not the point of discussion here. So here is an example which compares two different types of compartments. This study was conducted by Underwriters Laboratory. Underwriters Laboratory is the leading agency. It's an NGO private agency which basically does a lot of research and a lot of kind of develops a big repository of different tests. So if I'm trying to develop a system, fire resistance system, and for my building, I don't have to do the test myself. If that matches very closely with one of the tests that they have done, I can cite that and say that, okay, this system is similar to what they have done, and they have that data is available. You can just take a subscription from them. Data is available. So that data you can use to be used in your building. If you're using concrete, you're using steel, these are the similar materials that they might have used. So that's UL, what you see in that corner is, so thanks to them, this is not my data. So basically what they have done is, they have taken a room from the 1960s or 70s. So in those days, plastics were not so common in our furniture, in our day-to-day utility. So most of the material that they had used here was mostly wool, cotton, solid wood, those kind of materials. And here in the modern compartment, most of the furniture is made of synthetic materials, like your chairs are made of, right? So basically they lit fire at the same time in both these buildings. The fire is lit. I think if I can you spot the fire? You can see somewhere here, I think the fire is there, and here there is a fire. So fire is growing much more rapidly in the synthetic, in the traditional room. Here you can see some kind of a black smoke coming out. Here you can see the flame. So that is the first difference. Synthetic materials, they burn, they create lot more fumes. Much more toxic gases are released. But now within 1 minute, 1.5 minutes, you can see the flame has grown so big, because I think there was some curtain that was lit. Here also the curtain or some kind of a fabric was lit, but that is taking much longer, because it's typically cotton that burns much more slowly. And within 3 minutes, you can see the fire has grown really big. And now pay attention to this surface area. Here, you can see fumes coming out of here, right? Right, that was the flashover point, when everything started burning without being in contact with the fire. And within 4 minutes or so, the flashover has already happened. It's not, so 3 minutes, 40 seconds, flashover happened. This is a traditional room where the curtain is still burning. I think they had to use some different type of cameras. So at around 29 minutes, the fire was large enough, and now you can see the fire is spreading to everything very rapidly. So at around 30 minutes, the traditional room took fire. But the point here was that, okay, you should know the difference between synthetic materials and the traditional solid wood, cotton-based materials, how much heat they can release and how quickly the fire can spread. But also more importantly, you should visualize, you should be able to see and understand what flashover is. So typically for structures, when we deal with, we talk about fires which are close to flashover. We are not talking about a fire which is localized in a compartment. Until that point, it may be a concern from people's safety point of view. People need to be evacuated. But from a structural engineering point of view, there is not much that we need to do at that time.
Sir, will you please repeat which agency has done this?
Can we?
Which agency has done this?
Underwriters Laboratory. Underwriters, UL. Underwriters Laboratory. So flashover is typically has certain characteristics. A flashover will be ventilation controlled. Everything is burning. So fuel is willing to burn at a very high pace, right? What will be in shortage in typical flashover or post flashover fire, right after flashover? Oxygen. So oxygen will be in short supply. So they will be ventilation controlled. If you give more ventilation, fire will be more violent. If you control the ventilation, fire will be less violent. So heat release rate will be controlled by the amount of ventilation that is available. A lot of turbulence will be there. The benefit of that having that turbulence is that we can make the assumption that temperatures are almost uniform in the compartment, because air is rushing in, the fuel is burning, and all that is moving very rapidly in the compartment, and because of that, a lot of turbulence is there. So what does ventilation do? Basically, whenever there is a big fire, and we are talking about fire which is closer to or close to flashover point, typically the fire grows so large that windows, if there are glasses and something, they will break. Right? So if there are any windows, the glasses can't sustain that kind of a temperature. Within at around 200-300 degrees centigrade, they will become very soft, and also they will want to expand, and the thermal shock will also damage them. Right? So they will break and they will turn into openings, which will allow the air to get in. Sorry. Rate of burning will pretty much proportional to area of the opening and the height of the opening is under root. So basically what it is saying is that if I have two compartments, identical compartments, single window in both of them, same area in that window, but one window is a little bit longish, taller, the other one is a little bit wider, right? So which one will be allowing more air to get in fire? Same cross-section area, same area of the window, same size of opening.
The longer.
Why wider one?
It's not as can come.
No. So actually, we discussed that when we showed the picture of a building in fire, how the lower half was allowing the air to rush in, and upper half was allowing the fires to or flames to pop out, leap out. So having a longer shape helps air and flames to deal separately, so they don't interfere with each other. So airflow can be very smooth. Otherwise, if you make wider windows, then from a narrow space, both air has to get in and the flames have to go out. So there is not enough space and they will interfere, and that will obstruct the flow of air into the room. So air supply will be constricted. So it is not just the area of the opening. Area of the opening is important. On top of that, square root of height of the opening, right? So taller openings are more effective in allowing oxygen to get in than the wider ones. So then there may be some situations, again giving an example of like indoor stadium or something, where there are a lot of openings, there's a lot of space, the fire is never reaching the point where everything is burning, or a airport kind of a place. There you may have a situation when fire remains fuel controlled throughout. But in most of the other fires, which are compartment fires, office fires, commercial space fire, yeah, so it's almost always it is ventilation controlled fire, right? Air will be in short supply. That will control how much heat will be generated in the compartment, right? So of course, those rooms are not where humans can live anymore. When anyway, fire has grown too big, so it is not for humans to live now. We are talking about a much bigger fire. Nobody was safe in that compartment anymore. Okay, so that is when the fire is still growing. The fuel is burning at full pace, and the fire temperature will be almost uniform. Right? It will reach the mature level. At some point, eventually, the fuel will start burning out, getting consumed. Once this fuel starts getting consumed, then all the fires will go into decay phase. As you remember, I had shown a plot before. This one. So this is steady burning, almost a flat portion in the middle, and then it goes into a decay phase. A decay phase is basically when decay phase will be triggered when the fire has consumed majority of the fuel and only the leftover fuel is burning gradually. So smoldering and some other things are going on still, and then the fire will be again fuel controlled. So mostly in this part, fire is ventilation controlled. How much oxygen you supply. If you supply more oxygen, it will burn faster. If you supply less oxygen, it will burn slowly. In this phase, it is mostly fuel controlled because you have not started burning everything. In this phase, it is again fuel controlled, right? So flashover is just an instant. Post flashover is when the entire compartment is in fire. That is post flashover fire.
That means at point of ventilation is greater.
When you switch from fuel control to ventilation control, is that what you are saying? That is not exactly the definition of flashover, but usually that happens very close to that point, the switch from fuel control to ventilation control, because sometimes even a localized fire can produce enough smoke that you may not have enough oxygen supply, right? So then it may not be a fuel controlled anymore. It may still, a localized fire can also be ventilation controlled. So this is how a compartment fire typically goes through different phases. Wherein in a compartment fire we can have flashover, but in an open fire we cannot have flashover, as we discussed, right? So in an open fire, what happens is that heat radiation can be very high because fuel could be available in plenty. In a compartment fire, there is a limited supply of fuel. Open fire would be a forest fire, for example. A forest fire, there is no limitation of fuel. The fire can keep spreading as far as the forest goes. So, and there is no shortage of oxygen also. But still, the heat release rates will be high, but temperatures may not be that high. The reason for that is that heat is not confined. So if the heat can keep escaping, the temperatures of that fire will not be or may not be that high. So typically, forest fires don't produce such high temperatures for the same amount of fuel. You know. So average temperature in a open fire is lower. So open fire could be, typically we should not compare a forest fire because forest fire is a different, like at a different scale we are talking about. Let's say you take some furniture in a compartment and take it outside, dump it outside and light fire to it. Like holy Dahan kind of a thing. So you would know bonfire. So what kind of heat you will generate there versus what kind of what kind of temperatures you will generate in a compartment. Compartment temperatures will be very high in comparison to outside temperatures. Okay, and of course, since there is no flashover, they spread only through direct contact, right? If there is no direct contact, heat will escape. So there is no flashover point. And it's mostly fuel controlled because there is no shortage of oxygen outside. From structural fire point of view, sometimes fire in a compartment can be disastrous for the structure, but sometimes one compartment fire may not be bad enough. But there are enough examples in our lives we have seen where fire spreads from floor to floor. You know, World Trade Center building tower fires, you might have all seen the videos. Right. So yeah, so or any of the big fires, big tall buildings you may see. There are a number of examples. I have not included all the case studies because we are going to get into the designing also. So any tall buildings, if you look at when the fire accident happens, if there are not enough safety provisions, typically fire jumps and moves upward in a building. So that is a very common phenomenon that happens. Firefighters fight the floor where the fire started. By the time they are able to control that fire, it jumps from some window or somewhere, it jumps to the next floor. Okay, and it keeps moving up in the building. Same thing happened in World Trade Center building also. There were, from outside you couldn't see the fire so clearly. It was mostly smoke, what we could see, but the fire was traveling through the building. There was one particular building in that compound, World Trade Center 7. So there was the two tall towers, World Trade Center. You all know what I'm referring to, right?
Yes.
WTC collapse, right? World Trade Center collapse, New York, 2002, 2001, 9/11. So the two tall towers, which were known as Twin Towers or World Trade Center towers, they were hit by airplanes, but there are several neighboring towers which were also very critical, very tall towers, almost 57-story tall, 50-story tall. Several such towers were there in the neighborhood of those two buildings in the same complex. They also collapsed on the same day because of secondary effects. So the two buildings collapsed, the fire kind of spilled into some other towers because some debris fell into them. And then those buildings caught fire and they burned for several hours and they also collapsed. And again, you could see that fire was traveling through the stories, but you could not see the flames traveling from outside. So flames could travel from within the building also. There are enough openings inside a building. So what could be the sources of flames traveling or fire traveling within a building? Staircases are commonly used. So wherever you would see staircases in a building, you would always see a fire door between the staircases, right? So those fire doors with a strong glass kind of a thing, small opening with a thick steel door that is placed around the staircases, right? Those are fire doors basically. They are supposed to keep fire from passing through the outside and getting to the other part of the building. What else?
Conduits,
What conduits?
So ducts for
Ducts. So all these ducts that you can see, these ducts sometimes pass through the floor. Sometimes here we don't have that problem, I suppose, but maybe I'm not 100% sure though. Facades. So what happens is that flooring ends here. The facade is at some gap between the. So there is a gap between the flooring and the facade, and there is an opening in between, which helps you with air conditioning and all because it keeps the temperatures uniform. But it can be bad from fire point of view. The fire, it's very important that fire is restricted. In fact, nowadays the apartments also, if you see most of the apartments the way they are made, mostly they have more open shape kind of a thing. So drawing room, dining room, kitchen, they are all in one open area, right? So kitchen is the most common source of fire. But if the kitchen had a provision of closing it, there was a door or something, you could at least confine the fire for some time. At least people could escape. But if the kitchen is connected with the rest of the apartment, the rest of the house, there is a more chance or higher chances of fire spreading quickly to the rest of the compartment or rest of the apartment. Anyway, let's not digress too far. So basically, within a floor, when we talk about within a floor, fire can travel very easily. So whatever there is no, if there are no walls in between, we'll call it a compartment. So an apartment where the kitchen, drawing room, dining hall, they are all connected. That's not even traveling of the fire, because that fire can travel with smoke and with the contact directly. Between the rooms, the fire can spread within a compartment because of this HVAC duct. So for example, these ducts are coming from one room to another, and they can, the fire, smoke and these fumes can travel to another room and can initiate or ignite a fire in another room very easily, right? And then smoke and toxic gases can travel and can create the havoc. Typically, that is the most common way of fire traveling, or otherwise doors can be open. So when the doors are open, that can happen. But many times, another way of fire spread can happen through the walls also. Anybody can think of some way how the fire can spread through a wall? Sorry?
Yes.
Electrical conduits.
No, electrical conduits are still conduits. So like whether HVAC or electrical conduits, that is covered already. Fine. Through a wall.
If the paint is not provided over to having the chemical resistance, that might come fire resistance.
Paint as such, I don't know. Yeah, sorry.
Flash.
Flash point. Can you say the full sentence? I don't understand.
How within the room it is transmitting?
Within a room.
How within the room, through non-contact, it is getting that?
Oh, flashover. Generally, that doesn't happen between, because the fume has to be accumulated there for the fire to, for the radiation to get there. So heat energy gets transferred through the wall. So it's not really flashover.
Material in the wall collapses.
So if the wall collapses, that is definitely a case, but walls don't collapse that easily. I mean, it's not like the walls collapse because of fire typically. How would the radiation cross through the wall, go through the
The wall is thin, like the thickness is
Yeah.
less.
So radiation will pass.
I mean,
It's not the radiation.
aspect, but a lot of energy.
Correct. So basically what can happen, if the wall is made of thinner material, so if it's a combustible wall, forget about it. That's not even a question. If the wall can burn down, then that's not really a fire protection wall. So that's like putting a curtain. Forget about it. We are talking about walls which can actually hold fire. So if there is a wall that can prevent fire from going to the other side, the wall itself can heat up a lot. So if you're talking about 3 hours or 4 hours of fire, and if it's a, let's say 8 or 9 inch or 6 inches thick wall, right, it can heat up a lot. And the heat of the wall, let's say there is another thing on the other side of the wall which is combustible, let's say a curtain or some kind of a combustible material, a painting or a drawing or a canvas or something, or paper, the wallpaper, they can catch fire, right? Or a rug hanging on the wall, they can catch fire because of the contact. So it is mostly a conduction problem, not a radiation problem. So that's why when you say radiation, I kind of was not fully convinced, but I thought that you understood the idea. Your idea was correct. So the heat can seep through the fire, the wall, and create fire on the other side. That is one way. The other way is where the walls can crack under fire loading. Why should the walls crack? Thermal expansion. So thermal expansion is and shrinkages and other kind of things. So those are major culprits which can create cracks. Different components will expand and shrink and will heat up and cool down and heat up and cool down. So as the heat flows through it, it will create cracks in wall systems. And sometimes there can be openings in walls. So walls can be made of 2 or 3 components, and there are joints in between, and those joints can open up. Right? So if those joints open and they give an opening of 4 or 5 millimeters, that is big enough for the flames to pass through those. Because what is the flame looking for? Oxygen. It's not looking for gas, it's looking for oxygen, right? So wherever there is oxygen available, it will try to leap out of it and go to the other side and can create fire again. So that is the typical way the fire spreads within a floor. How does the fire spread between the floors? Between the stools. Cracks in slab systems. So slab systems, nowadays we are going with this hollow core slabs, which are basically joint floor systems. This is not a monolithically cast system, right? It's separate floors, separate slabs, placed together. Then you put a top layer of shotcrete or something on the top layer, but in a fire condition where there are a lot of deformations taking place, that top layer can be brittle and can break off, and then you are getting a gap in between. That gap can allow the fire to seep through. Very good. That is one. Second one is, of course, ducts,
The heat
etc.
that was leaping out of the window. That can also.
So through windows also, and through the gap between the facade and the wall system. So facade and the floor system. So because in this building, for example, you can see the facade is basically attached to the wall outside, and this is the glass which is attached to this one. But there is no gap between the floor. If you see at the bottom, there is no gap between the wall and the floor. So generally, seems like a safe place. But we don't know. Maybe there is a small gap over there under fire. We don't know how much spacing it can create, and the fire can try to leak out from there. Right. So I'm assuming that that gap is close enough and it's tightly packed. But still, there is such a possibility. Yes.
Hollow core slabs. There are two slabs or there is one slab with one.
You are familiar with hollow core slab systems? Have you seen them? So basically, how many of you have seen or looked at hollow core slab systems? Hollow core slabs? Not necessarily bubble deck. Bubble deck is a different option. So basically, hollow cores are. I'll have to draw it. So this is basically an innovation in the direction of precast construction, right? So we don't want to do in situ casting a lot. We want to be able to move to the next floor as quickly as possible. And in order to achieve that, what we do is we precast some slabs, and those precast slabs can be solid slabs also. But people have worked out that generally the strength consideration does not govern the design of slab systems. Which consideration governs the design typically? Serviceability, right? So when the serviceability is going to govern, let's not put too much concrete into it. What we do is we cut holes, leave gaps, right? So basically we put some tubes at the time of casting itself, and then we cast concrete in it that those tubes run through, right? So those are hollow gaps. So that's why it's called hollow core slab. And they are fixed length. That length is basically where you will have your beams. So this is where the supports will be, right? And then the next slab will be next to it, and then another slab will be right next to it. So you put several slabs next to each other. Then on top of that, you put a top cover, kind of a cast one layer of concrete to just make this whole thing monolithic. But majority of the structure is not monolithic; they are separate. So if they are separate and there is a fire here, because of the fire, the slab may want to bend, deform, and when it wants to bend, it will not necessarily bend by the same amount as the next slab, and then this joint will open. This joint will have a shearing, and then from there the fire can seep.
Now, hollow tubes are typically some material.
No, typically not. So their hollow tubes are useful because they can also work as conduits. So you can pass various types of piping and electric wiring and everything from those conduits. So that way it is used.
Following is that to reduce the weight of dead load.
Primarily, yes. Because see, the concrete sitting near the neutral axis
Does not contribute.
does not contribute in flexure much. It helps in shear, but generally shear resistance for slabs is hardly ever a concern.
Yes.
So then we don't have to really. Okay, I think I need to speed up a bit. Yeah, 1.5 hours is past. So there are 2-3 types of fires. We discussed open fire, we said, but that is generally not a concern for structural engineers. Open fires don't affect structures. Structural fires, again, within a structure there can be localized fire, right? A localized fire is where the fire starts from one end but cannot spread to the entire compartment. Compartment can be very large or for some reason. So in such cases, models are slightly more complicated because fire is not uniform. The post flashover fire in a compartment is the most fearsome fire and relatively easy to approximate, right? Because the fire is so severe that, or the turbulence is so high that we can assume the temperatures to be more or less uniform. Right? So because of that, we can typically model fire, which is a post flashover fire, and we call it a single zone model. Typically, we use something called a one zone model, single zone model, and with that model, we can model it. So there are 2 or 3 different categories of fire models. One which the very basic ones, we call them nominal fire models, which is basically used by structural engineers. We love it, unless you are a structural fire engineer. If you are a structural fire engineer, you may want to go into simple model and advanced models a little bit. So nominal fire models from structural engineering point of view is basically saying what temperature fire has. So fire becomes a single entity. There is no variety in fire. It's a single fire. What temperature does it have? Tell me the temperature. So at any given instant, it has a constant temperature, a single temperature value, right? So then there are 2-3 categories within that. Typically, we have a standard fire curve. Then there are external fire curve. External fire curve, when we are referring to, it might be of relevance to structural engineers if we are talking about a bridge fire, for example, right? So there is a fire under a bridge or over a bridge. Over a bridge fire, sometimes it may be relevant, but not so often. Under a bridge fire can be many times important. So even an open fire, external fire, can be relevant to us under a bridge kind of a situation. Standard fire curve is typically for compartment fires, right? And hydrocarbon fire curve is again a compartment fire, but which is led by hydrocarbons. So if it's used as a storage for petrol, diesel or something, then we would call it a hydrocarbon fire. Yeah.
What does the word external accounts for?
Open fire. Open fire. External is basically not inside a compartment. The fuel is sitting outside, right? So there have been several accidents. In case you are not familiar with, in the US, in the last 10 years, I have heard of at least 3 major accidents where the bridge almost collapsed or collapsed completely. So major severe damages to the bridge structures because of fire. Fire was basically lit under the bridge. So there was one incident when a tanker, a diesel tanker which was carrying diesel, it hit the column, the pier under the bridge, and caught fire. That led to a big fire under the bridge. That is a very plausible scenario. It happened, but people had never accounted for it. There was one more scenario where there was a bridge under which some construction material was stored. That construction material included a lot of this polyurethane foam kind of a thing, and that caught fire. And then it, again, mostly polyurethane fire is a hydrocarbon fire, right? It's very high temperature, very high calorific value, and very low density, so burns very quickly, and bridges are not protected for fire, right? Bridges generally are not required to be protected for fire. You can see steel exposed almost, just painted. So those bridges, especially steel bridges, they are particularly vulnerable, right? Then there is a simple fire models. So simple, basically, again, they are fire curves, basically temperature curves, but parametric curves in a way, right? So there are 2 or 3 of them. Then there is advanced fire model, which is the zone model, which is basically says, you remember when I was talking about a localized fire? So in a localized fire can be started from here, but the zone, when we divide the fire, we'll say upper zone and lower zone, because that temperature is not that big a problem for us. It is the heat that accumulates in the upper half that can become a structurally problematic thing. So the upper parts can be at a higher temperature, the lower parts can be at a lower temperature. So zone model can be used. Single zone model will be useful for a post flashover kind of a fire. 2-zone model will be useful for a pre-flashover fire, kind of a localized fire. And then CFD based, so computational fluid dynamics, you add chemistry to it, and such kind of models are available. If anybody is interested in learnings, many of them are available for free. So you can kind of download and try your hands on it. So when we talk about standard fire, the first nominal fire curve was standard fire. Standard fire is typically what we follow in India is ISO 834, right? So ISO 834 is the code that is, we borrow most of the fire provisions from there in the Indian code. This solid line here shows that curve. So you can see it has a very high rate of fire growth, temperature growth. In the first 10 minutes, the temperature goes to almost 800 degrees centigrade. 10 or 15 minutes, and then gradually it stabilizes and goes almost up to 1100 or 1200 degrees centigrade. Americans use ASTM curve. This is the ASTM curve. That also goes almost up to 1190 degrees centigrade or something, right? So they follow each other very closely. If it's a hydrocarbon curve, hydrocarbon fire, that also goes to 1100 degrees centigrade, but it peaks very quickly. The temperature rises very fast because the calorific value is high and density is low. Right? And then external fires, as we had mentioned, if it's an open air fire, the temperatures will not be very high. So that's why you can take this kind of a curve, which is this dotted line, that can be used. So Eurocode gives both this hydrocarbon and external fire curves in addition to its ISO 834 curve. So ISO 834 curve is available in ISO. It's used by British standards, used by Eurocode, used by Indian code also. So that is universally accepted. Americans use ASTM E119 curve. Okay. A typical fire, we had seen this is how a typical fire in a compartment looks like. You saw this one, this is a standard fire curve. So if you overlap the two, this is how this, if I try to match the two, this is how it would be approximately. So basically what we are saying, we will ignore the initial ignition and initiation phase, initial growth phase. After the fire is very close to flashover, that's when we will start from. So we will basically take this point and then draw it backward wherever it meets. That will be the point of initiation. And then we will follow, and there is no decay phase in the standard fire, right? So there is no reduction in temperature. The temperature keeps going up or maintains at around 1100 to 1150 degrees centigrade. The temperature maintains at the constant value but does never come down. That is the standard fire curve, right? There are a lot of problems with this standard fire curve kind of an approach. I don't have time today to discuss all that. Basically, the cooling down of fire, it has been studied, is almost as detrimental to structural safety as the heating is. Right? So it's not just the heating. It is during the cooling, many structures have been found to collapse, not just the heating. So if we do a standard fire test where we just heat it, and we heat it for 1 hour, and we say we have heated it for 1 hour, everything was safe, you take away your specimen, everything is safe, you might be at fault, like you might make a mistake there, because you have to wait for it to cool down also, right? And then study the behavior. But presently, that is the standard procedure to test, and most of the international standards accept it. You just heat it and test it. Then those were the nominal curves, right? So ISO standard, ASTM standard, British standard, Indian standard, they are copy of ISO standard. On top of that, there is this more complex type of fire curves that are available. Basically, you saw this curve, right? So we are trying to get closer to this curve. Standard fire doesn't get very close. Then we will try to get closer to it by including the decay phase also, and how rapidly it increases. So in the standard fire, how rapidly this slope increases is not a variable. That's a constant value. This is a standard fire curve, fixed curve. It does not, there are no parameters that will control this curve. But in reality, every compartment is different. If the compartment walls are made of brick versus if the compartment walls are made of the dry wall, the gypsum board, the two will behave differently. Brick will absorb a lot more heat, right? So the compartment temperatures will be lower for a significant amount of time, whereas gypsum board will reflect most of the heat back. So temperature in the compartment will be higher. It will not absorb much heat. Similarly, how many windows does the compartment have? We have discussed so much about the windows and everything, but standard fire curve does not account for the window size or window number of windows. So that all those things can be incorporated in the curve. So there was first effort in that direction, again primarily a parametric study, experimental empirical study in the 1970s, where these two people who were, most of this research was done in Scandinavian countries and like Northern Europe. A lot of research has happened in fire in the Northern Europe. So they basically came up with these 2-3 parameters. The FV parameter is basically ventilation factor. You remember we had talked about ventilation is proportional to how much area of ventilation you have, how much window area you have, and square root of how high the ventilation is, how high the windows are, tall the windows are. So that comes as a parameter plus normalized against the total area of the opening. So, sorry, total area of the enclosure area. What you can see is that they have come up with these nice equations to predict the fire time temperature. As the time grows in hours, the temperature increases and then decreases. So if the opening size is large, FV is large versus FV is small, you can see for the same compartment is having the same amount of fuel, sizes are same, boundaries are the same type of walls. Only in one case the windows are allowing more air to come in. In this case, windows are allowing less amount of air to come in. This fire is of low intensity but long duration, and this fire is of high intensity and short duration, right? So not all fires are the same, and that is critical. And sometimes it may appear that maybe I should design for this one or maybe I should design for this one. It may not have any obvious answers to it. In some scenarios, you may find that this type of a fire may be more critical for the structure, and in some scenarios this type of a fire will be more critical, right? Higher temperature is bad, but also long duration of fire is also bad, right? So you cannot make a direct judgment by looking at the two curves that, okay, this is safer. That may not be the case. So ideally, one should always check for the possibility of a fire for the given compartment, not assume the type of fire it will have, right? But there are too many variables. How many windows a compartment would have, the designer, structural designer doesn't know. Structural designer is not even involved in the designing of the windows. That is done separately, completely by different office. Therefore, even though these are important, the process is so cumbersome, we don't really indulge into this process. Similarly, surrounding. So, sorry, this is, yeah.
Area of the opening of the buildings,
Yeah.
the area of the building, that were similar for the three cases.
No,
Area.
no. Area of the windows, it differs.
Yes.
Yeah. So between, let's say the shape is the same, window shape is the same, then
But there are a number of windows. More windows in a room, there may be less windows in a room.
So I don't know exactly how they varied this number. It can be varied by increasing the length of the window, because if you increase the length of the window, FV factor will increase. So this is the FV factor,
Yes, height.
right?
Yes.
So HV comes into that one. Or area can be increased. Area of a single window can be increased, or area of several windows, like several windows can be provided with different small areas. I don't know exactly how they varied it, but ultimately they plotted it against FV. So FV from here to here, you can see opening has increased by about 6 times. FV factor has increased by about 6 times, right? And because of that, you could see that fire could be much more rapid. It makes sense, right? So when oxygen is available in plenty, the fuel will burn very rapidly. So within a few minutes, it will reach a very high temperature. It will burn at the highest pace it is possible. But then soon, the fuel will run out, and then you will have a decay phase that will start quite early. So within 30 minutes, the decay phase started. Whereas in this case, decay phase started almost at around 2 hours. Here they changed the fuel, amount of fuel that was available, and you could see the fuel in this part of the fire, it was a spreading fire, so that would not really matter how much fuel is available. But after the fire had spread to the entire compartment, post-flash, then basically the amount of fuel availability started to govern. So if the fuel was very limited, the fuel started to run out, and they started to have a decay phase. But if there was plenty of fuel available, then it didn't run out that easily, right?
But they have not studied for different types of fuels.
Different types of fuels they have not studied here. I mean, this particular, and this is basically parametric curves. So this is not how they developed this equation. From these equations, they have got these curves. How they got these equations must be a lot of research must have been done in the background. How they?
So the amount of fuel,
Yes.
amount of fuel is increasing. The 50
Yes.
to 500.
Yes.
The variation of the fuel load.
Yeah, fuel. So the fuel is being counted in terms of joules, megajoules. So it is megajoules per meter square. They are saying no matter what fuel you use, as long as it has same number of joules, that's what matters. So, but see, these are equations given by them. This is not the real experiment. They did hundreds of experiments before. From there, they got these parameters, and from those parameters, there are some equations. Those equations I have not written here.
They got the conclusion that the amount of the fuel affects the
Right. There are other set of equations which also give kind of a parametric curves. I'll not go into this one. This is again very commonly used nowadays. If you are planning to use any such parametric equations for predicting fire, this would be the one that you can very easily refer to. It's very nicely detailed. One second.
In that slide, in the curve. Here, we can see that the higher calorific value of the fuel will have a higher fuel load
Yes.
from the equation. So, can we conclude that if the fuel is of higher calorific value, it will have the same curve that the upper curve is?
This type of curve.
No, sir. In the down curve.
This type.
So
That's what it is saying. Na? So basically, they are not saying how they increase the fuel load. You can increase the fuel load by increasing mass, or you can increase the type of fuel. That's what they are saying. So they are basically reporting this curve only in terms of megajoules per meter square. But of course, it will vary, because as we had seen, the Q value, you remember Q was a function of T square divided by K. Heat release was a function of K. So that K has not come into this picture. So that K is somehow standardized in these equations. They are not allowing that variation of Q, variation of K. Okay, so you can go to Eurocode parametric curve. You can just search on the internet. I have not written the reference here. It's, I think, Eurocode 2. You just look for Eurocode 2, ECEN 2. 1998 2, something like that. So there, a lot of these equations are available, wherein O stands for opening factor. So you remember the first set of equations where we had the curves where we had shown a intense fire with short duration and long fire with, low intensity fires with long duration. So that same thing you can get with these parametric curves also. They also have three factors to be brought in. One is thermal inertia. That is basically what kind of walls you have and what kind of slab you have. If your walls and slab are made of heavier materials, more denser materials, then they will absorb much more heat. Similarly, fuel load, how much fuel load you have and how much opening space you have, right? So all those can be fed into these equations. Those equations I have not reported here. Basically, you can get this kind of a curve. So those were, so far we have seen two types of models. Nominal model was standard fire curve basically. So where you had just one curve for all tests. Right, so one curve for compartment, the other curve Eurocode gives you for external fire. So two curves basically, right? Then we got to simpler models. Simpler models take into account the surrounding wall density, etc. It takes into account the openings, etc. How much fuel is actually available, and then you can develop the exact curve, which will have the increasing phase, then declining phase, all that thing, right? So these two models. The third model is more complex one, where you really want to account for how much fuel density there is, and you really want to do a physics-based energy balance, right? So these are one zone model, zone-based model, or one zone or two zone model, and then CFD-based model. So CFD-based model is, of course, like that's the most complex one, closest to the real physics that you can have. For CFD-based model, if you want, you can download this software called FDS. It is available for free on the NIST website. NIST is National Institute of Standards and Technology. Technology, right? Standards and Technology. So that is available, software available freely. Even the manual is available. You can download, you can teach yourself a little bit. And it's quite handy to get an idea about what type of temperature curves can be expected. Time temperature curves can be expected. Otherwise, there are one zone or two zone models. Again, there are mostly softwares, so you have to download that software, and some of them are available for free. And you can try your hands on and try to get what temperatures you can expect for what kind of fuel density.